Tonight, we're going to embark on an impossible journey, a voyage that no human has ever completed and perhaps never will. We're going to fly through every single planet in our solar system, not past them, not around them, but straight through their clouds, their storms, their crushing atmospheres, and their mysterious cores. It's a journey that would destroy any spacecraft we've ever built. A trip that defies the laws of physics as we know them. But here, in this quiet moment, we can let our imagination carry us where no rocket ever could. Before we begin this cosmic adventure, feel free to comment your time and location below. It's always amazing to see when and where we're all watching from or gently drifting off. The visuals are here for you, but there's absolutely no problem if you doze off midway through the video. Feel free to close your eyes, breathe deep, and let your mind soar through the solar system at whatever speed feels right. I would love and encourage you to watch until the end to experience every world we'll visit. But if sleep finds you somewhere between Venus and Saturn, that's perfectly fine too. If you find comfort in these gentle explorations of space, I'd be grateful if you'd consider subscribing and liking this video. It helps the algorithm find more curious minds like us who wonder what it would be like to touch the face of Jupiter or fall through the rings of Saturn. Let's begin our impossible voyage. We're going to start close to home and work our way outward, visiting each planet in order from the Sun. Some of these worlds will welcome us with gentle breezes. Others will try to crush us, burn us, freeze us, or tear us apart with winds faster than sound. But tonight, we're invincible travelers, immune to heat and cold, pressure and radiation, free to explore every layer of every world in our solar system. Our first destination sits closest to the Sun, baked in radiation, spinning slowly through space with a surface that tells stories older than life on Earth. This is Mercury, the smallest planet in our solar system, and one of the most extreme places you could ever visit. As we approach, the first thing that strikes you is how utterly alone it looks. No moons orbit this world. No rings grace its equator. Just a grey, cratered sphere that looks remarkably like our own moon, only somehow more ancient, more weathered, more scarred by billions of years of cosmic bombardment. We begin our descent toward the surface, and immediately the temperature starts to climb. The daytime side of Mercury reaches temperatures of 430 degrees Celsius, hot enough to melt lead, hot enough to make zinc boil away into vapor. But Mercury has a secret. Because it rotates so slowly, taking 59 Earth days to complete a single spin, and because it has virtually no atmosphere to distribute heat, the night side plunges to minus 180 degrees Celsius. It's a world of impossible extremes, where standing in sunlight would incinerate you while standing in shadow would freeze you solid. As we pass through the thin wisps of what Mercury calls an atmosphere, we barely notice it. This isn't really an atmosphere in any meaningful sense. It's what scientists call an exosphere, so thin that atoms here, potassium, bits of oxygen, rarely collide with each other. There's sodium and hydrogen, all of it captured temporarily from the solar wind before being blown away again into space. The total mass of Mercury's entire atmosphere wouldn't fill a large swimming pool on Earth. We continue downward, approaching the surface, and the landscape becomes clearer. Vast impact basins stretch across the horizon. The Caloris Basin, one of the largest impact craters in the entire solar system, spreads out beneath us like a frozen sea of ancient violence. When the asteroid or comet that created this basin struck Mercury billions of years ago, the impact was so powerful that it sent shockwaves completely through the planet, creating strange rippled terrain on the exact opposite side of the world. Imagine an impact so violent that the entire planet rang like a bell, the surface buckling and cracking from the force transmitted through thousands of kilometers of solid rock. We descend through the surface now, passing through layers of rock and metal that tell the story of Mercury's formation. Unlike Earth, Mercury has an enormous iron core that takes up about 3/4 of the planet's diameter. This core is partially molten even today, generating a weak magnetic field that creates a tiny protective bubble around the planet. As we sink deeper into Mercury, the pressure builds and the composition changes. The outer layers are mostly silicate rock, similar to Earth's crust and mantle. But as we approach the core, iron becomes dominant. The core itself is a mystery that scientists are still trying to understand. It's far larger than it should be for a planet this size. One theory suggests that Mercury was once much bigger, perhaps similar in composition to Earth, but a catastrophic collision early in its history stripped away much of its rocky outer layers, leaving behind a world that's mostly metal. Another theory proposes that intense solar radiation in the early solar system vaporized the lighter elements, leaving Mercury with its current metal-rich composition. We pass through the solid outer core and enter the liquid inner regions where temperatures reach several thousand degrees. Here, convection currents of molten iron generate Mercury's weak magnetic field, about 1% as strong as Earth's, but still enough to deflect some of the solar wind. At the very center, we might find a solid inner core, similar to Earth's, where the pressure is so immense that iron freezes despite the incredible heat. Emerging from the other side of Mercury, we take one last look at this scorched world. Despite being the closest planet to the Sun, Mercury isn't the hottest planet in the solar system. That distinction belongs to our next destination, a world wrapped in a toxic atmosphere so thick it creates temperatures that exceed even Mercury's sunlit surface. We leave Mercury behind and travel inward toward the Sun, then outward again to our second planet. Venus appears before us like a pale yellow jewel, completely shrouded in clouds. From space, Venus is beautiful, reflecting more sunlight than any other planet, shining brightly enough to cast shadows on Earth. But this beauty is deceiving. Venus is perhaps the most hostile environment in our solar system, a hellscape hidden beneath those innocent-looking clouds. As we approach, we can see the clouds rotating around the planet much faster than the planet itself rotates. Venus has the slowest rotation of any planet, taking 243 Earth days to complete one spin. But the upper atmosphere whips around the planet in just 4 days, driven by winds reaching 300 kilometers per hour. This phenomenon, called superrotation, is still not fully understood by scientists. We begin our descent into the cloud tops, and immediately we understand why Venus is so difficult to explore. The clouds aren't made of water vapor like Earth's clouds. They're made of sulfuric acid, concentrated sulfuric acid droplets that would dissolve most materials on contact. These clouds form a layer roughly 20 euring the surface from kilometers thick, completely ob-SC view. No sunlight penetrates these clouds' invisible wavelengths. Any solar panels would be useless here. The cloud deck is illuminated by a dim orange glow, creating a perpetual twilight that never changes. As we descend deeper, the temperature and pressure begin to rise dramatically. The atmosphere of Venus is 96% carbon dioxide, creating the most extreme greenhouse effect known in our solar system. The carbon dioxide traps heat so efficiently that surface temperatures reach 470 degrees Celsius, hot enough to melt lead, hot enough to make some metals glow red hot. And unlike Mercury, where you could escape the heat by moving into shadow, Venus maintains this temperature day and night, at the equator and at the poles. The thick atmosphere distributes heat so effectively that temperature variations across the entire planet are minimal. We continue sinking through layer after layer of atmosphere. The pressure builds steadily. At 10 kilometers above the surface, the pressure is already equal to Earth's sea level. At 5 kilometers, the time we reach the surface, it's doubled. Biatmospheric pressure is 92 times greater than Earth's, equivalent to being 1 kilometer deep in Earth's oceans. This pressure is enough to crush most submarines. It's enough to make carbon dioxide behave almost like a liquid rather than a gas. The surface of Venus finally becomes visible, illuminated by that strange orange glow filtered through 60 kilometers of dense atmosphere. The landscape is unlike anything on Earth. Vast volcanic plains stretch to the horizon, covered in frozen lava flows. Enormous shield volcanoes rise from the surface, some of them larger than any volcano on Earth. Martmont's towers 8 kilometers above the surrounding plains, and unlike Earth's volcanoes, which are shaped by plate tectonics and erosion, Venus's volcanoes tell a different story. Venus has no plate tectonics as we understand them. The entire surface appears to be a single solid shell, and every few 100 million years, the entire planet seems to resurface itself through massive volcanic eruptions. The current surface is relatively young, perhaps only 500 million years old, suggesting that at some point in Venus's recent past, the entire planet was covered in molten lava. Why this happens is still debated. Perhaps heat builds up beneath the solid crust until the pressure becomes too great and the entire surface breaks apart and melts. Perhaps there are cycles of volcanism we don't yet understand. We sink through the surface now, passing through layers of volcanic rock. The composition is similar to Earth's basalt, rich in iron and magnesium. As we descend, we pass through what might be Venus's crust and mantle. Without plate tectonics, Venus's interior structure is probably simpler than Earth's, without the complex layering created by subduction zones and continental drift. The mantle is likely a thick layer of silicate rock, solid near the surface, but gradually becoming more plastic and flowing at depth. Deeper still, we approach Venus's core. Scientists believe Venus has an iron core similar to Earth's, though probably without the internal structure of separate solid and liquid regions. Venus has no magnetic field, which suggests either that its core is completely solid, completely liquid, or that it rotates too slowly to generate the convection currents necessary for a magnetic dynamo. The core temperature might reach 5,000 degrees Celsius, and the pressure could exceed 3 million times Earth's atmospheric pressure. Emerging on the far side of Venus, we look back at this toxic world with a mixture of fascination and relief. Venus is a cautionary tale of what can happen when a planet's climate spirals out of control. Scientists believe Venus might once have had oceans like Earth, but a runaway greenhouse effect evaporated them billions of years ago, leaving behind the inferno we see today. Our next destination is home. Earth, the only planet we know that harbors life, the only world in the universe where you can breathe the air and drink the water and watch clouds drift peacefully across a blue sky. As we approach from space, Earth looks impossibly beautiful. The blue of the oceans, the white of the clouds, the brown and green of the continents, all of it swirling together in patterns that change by the hour. From space, you can see weather systems forming, hurricanes spinning, the Terminator line dividing day from night, sweeping across the surface. We begin our descent, and unlike Mercury and Venus, Earth greets us with a thick but breathable atmosphere. The air is mostly nitrogen and oxygen, with just enough carbon dioxide to keep the planet warm, but not so much that it creates a runaway greenhouse effect. The temperature at the surface averages 15 degrees Celsius, perfect for liquid water to exist. As we pass through the upper atmosphere, we feel the thin wisps of air gradually thickening. The mesosphere surrounds us now, where temperatures drop to their lowest point in Earth's atmosphere, cold enough that water vapor freezes into ice crystals, creating the strange glowing clouds called noctilucent clouds. These clouds are so high and so thin that they're invisible during the day, but at twilight they catch the sun's rays long after sunset, shimmering like silver threads against the darkening sky. We continue downward through the stratosphere, where ozone molecules absorb ultraviolet radiation from the sun, protecting all life below from harmful rays that would otherwise sterilize the surface. This layer is warmer than the mesosphere above it, precisely because of this absorption, creating a temperature inversion that helps keep weather confined to the lower atmosphere. Without this ozone shield, Earth would be as barren as Mars, as lifeless as Venus. The troposphere welcomes us next, the layer where all of Earth's weather happens. Here we pass through towering cumulonimbus clouds that stretch from near the surface all the way to the stratosphere. Lightning flashes within these massive storm systems, transferring energy between the clouds and the ground in brilliant arcs of electricity. The air here is thick and moist, carrying water vapor that will fall as rain, feeding rivers and lakes and forests below. As we approach the surface, the diversity of Earth becomes overwhelming. Mountain ranges thrust upward from the crust, the Himalayas still rising as the Indian plate crashes into the Eurasian plate. Deep ocean trenches plunge downward, the Mariana Trench reaching nearly 11 kilometers beneath the waves. Deserts spread across continents, rainforests pulse with life, ice caps gleam white at the poles. This is a world shaped by plate tectonics, by flowing water, by life itself, all working together to create an ever-changing surface unlike anything else we've seen. We descend through the ocean now, passing through layers of water that grow darker and colder with depth. Sunlight penetrates only the first 200 meters, creating the euphotic zone where photosynthesis can occur. Below this, the twilight zone stretches down to 1,000 meters, where strange bioluminescent creatures create their own light in the darkness. Deeper still, the midnight zone holds mysteries we're only beginning to understand. Creatures adapted to crushing pressures and eternal darkness. The ocean floor spreads beneath us, and we sink through it into Earth's crust. Unlike Venus, Earth's crust is broken into massive plates that slide over the partially molten mantle below. At mid-ocean ridges, new crust forms as magma wells up from below. At subduction zones, old crust slides beneath continental plates, melting and recycling back into the mantle. This constant motion, this endless recycling of Earth's surface, has shaped our planet for billions of years. We pass through the crust and enter the mantle, a layer of hot rock that flows like taffy over geological timescales. The upper mantle is solid but plastic, flowing in vast convection currents that drive plate tectonics at the surface. Deeper in the mantle, the pressure becomes so intense that the crystal structure of minerals changes, becoming denser, packing more efficiently. The lower mantle extends down nearly 3,000 kilometers, gradually increasing in temperature and pressure until we reach the boundary with the core. The outer core greets us with liquid iron and nickel, flowing in massive currents that generate Earth's magnetic field. This magnetic field extends far out into space, creating a protective bubble called the magnetosphere that deflects most of the solar wind, preventing our atmosphere from being stripped away like Mars's atmosphere was billions of years ago. Without this magnetic field, Earth would be uninhabitable, the surface bombarded by radiation, the atmosphere slowly leaking into space. We sink through the outer core, feeling the temperature rise to nearly 5,000 degrees Celsius, as hot as the surface of the sun. The pressure here is immense, millions of times greater than at the surface. Finally, we reach the inner core, a solid sphere of iron and nickel, kept solid by pressure so intense, it overcomes the extreme heat. This inner core rotates slightly faster than the rest of the planet, creating complex interactions with the outer core that scientists are still working to understand. Emerging on the far side of Earth, we take one last look at our home world. The thin blue line of atmosphere, the white swirl of clouds, the deep blue of the oceans, all of it precious beyond measure. Earth is the only place in the universe we know of where you could exist without a spacesuit, where you could breathe deeply and feel rain on your face and watch a sunset paint the sky in colors that no other world can match. But our journey continues outward. Our next destination is the red planet Mars, a world that once might have been as hospitable as Earth but lost its atmosphere billions of years ago, leaving behind a cold desert where ancient riverbeds cut through rust-colored rock. As we approach Mars, the first thing that strikes you is how small it is. Mars has roughly half the diameter of Earth, giving it only about 1/10 of Earth's mass. From space, it appears distinctly red, colored by iron oxide dust that covers much of the surface. We begin our descent through Mars's thin atmosphere, and immediately we notice how different it is from Earth's protective blanket of air. The atmospheric pressure at the surface is less than 1% of Earth's sea level pressure, so thin that liquid water cannot exist on the surface. It would either freeze or boil away, depending on the temperature. The atmosphere is mostly carbon dioxide, with traces of nitrogen and argon, but there's so little of it that it provides almost no greenhouse warming. Surface temperatures average -60 degrees Celsius, though they can rise above freezing at the equator during summer days. As we descend, dust devils swirl across the surface below us, visible even from high altitude. These towering vortices of dust can reach several kilometers high, created by the sun heating the ground unevenly. During certain seasons, dust storms can grow to engulf the entire planet, turning day into twilight and lasting for months. The dust is fine, almost like talcum powder, and it gets into everything, coating every surface, filling every crevice. The surface of Mars spreads out beneath us, a landscape of contrasts. The northern hemisphere is mostly smooth lowland plains, ancient ocean basins that might once have held vast seas of liquid water billions of years ago. The southern hemisphere is heavily cratered highland terrain, similar to the lunar highlands, preserving impacts from the early solar system. The boundary between these regions is one of the most dramatic elevation changes in the solar system, a cliff that stretches around nearly half the planet. We pass over Olympus Mons, the largest volcano in the solar system, a shield volcano so massive it would cover the entire state of Arizona. It rises 21 kilometers above the surrounding plains, nearly 2.5 times the height of Mount Everest, with a base 600 kilometers across. The summit holds a caldera 85 kilometers wide, large enough to swallow the city of Paris. This volcano was built over billions of years by countless eruptions, each one adding another layer of lava to the growing mountain. Nearby, the Tharsis region holds 3 other massive volcanoes, all of them extinct now, all of them testament to a time when Mars was geologically active. But unlike Earth, Mars has no plate tectonics. These volcanoes formed over hot spots in the mantle and stayed in place, growing larger and larger over geological time. On Earth, plate tectonics would have moved the volcanic islands away from their hotspots, creating chains like Hawaii. On Mars, the lack of plate movement allowed single volcanoes to grow to enormous size. We descend toward Valles Marineris, a canyon system so vast it makes Earth's Grand Canyon look like a small scratch. This enormous rift stretches over 4,000 kilometers across the Martian surface, roughly 1/5 of the planet's circumference. In places, it's 7 kilometers deep and 200 kilometers wide. If Valles Marineris were on Earth, it would stretch from New York to Los Angeles. The canyon was probably formed billions of years ago when the Tharsis region was uplifting, stretching, and cracking the crust, like pulling apart a piece of bread dough. We fly along the canyon floor, passing through layers of rock that record billions of years of Martian history. Ancient river channels cut through the canyon walls, evidence of a time when liquid water flowed across Mars. Some of these channels are enormous, suggesting catastrophic floods that dwarfed anything Earth has ever experienced. Scientists believe that underground ice might have melted suddenly, perhaps from volcanic heat, releasing vast quantities of water that carved these massive channels in a matter of days or weeks. We continue our descent, sinking through the surface into Mars's crust. The crust is thicker than Earth's, perhaps 50 kilometers thick on average, composed mostly of volcanic basalt in the lowlands and older, more complex rock in the highlands. Unlike Earth, Mars's crust is a single solid shell, no plates sliding and colliding, no constant recycling of rock. This means the surface preserves features billions of years old, a geological record that goes back to the very beginning of the solar system. As we sink deeper, we pass through the mantle, a thick layer of silicate rock similar to Earth's mantle, but cooler and more rigid. Mars cooled faster than Earth because of its smaller size, and the mantle no longer flows in the convection currents that drive plate tectonics on Earth. The lack of internal heat also means Mars has no active volcanism anymore, no magnetic field generated by a liquid core. The planet is geologically dead, frozen in time. We approach the core, and here scientists face a mystery. Mars once had a strong magnetic field, evidence preserved in magnetized rocks in the ancient southern highlands. But the field disappeared roughly 4 billion years ago. The core is probably made of iron and nickel, like Earth's core, but it must be either completely solid or completely liquid, unable to generate the convection currents needed for a magnetic dynamo. Some scientists think the core might be partially liquid, but not convecting because it's too cold, or because it contains too much sulfur, which lowers its melting point. The core extends roughly half of Mars's radius, smaller proportionally than Earth's core. The temperature at the center might reach only 2,000 degrees Celsius, much cooler than Earth's core. The pressure is also much lower, perhaps only a few 100,000 times atmospheric pressure, rather than the millions of atmospheres at Earth's core. We pass through the core and emerge on the far side, leaving behind this ancient world that tells the story of what happens when a planet loses its atmosphere and its magnetic field. Mars is a world of lost potential, a planet that might have developed life billions of years ago when it had liquid water on its surface, a thicker atmosphere, a warmer climate. But without plate tectonics to recycle carbon dioxide, without a magnetic field to protect its atmosphere from the solar wind, Mars gradually lost its atmosphere to space. The water froze or escaped, the climate grew cold, and whatever chance Mars had for life slowly disappeared. Our journey continues outward now, past the asteroid belt, toward the giant planets that dominate the outer solar system. Our next destination is Jupiter, a world so massive that all the other planets in the solar system could fit inside it with room to spare. From a distance, Jupiter appears as a massive globe banded with clouds, the great red spot visible as a rust-colored oval larger than Earth itself. As we approach Jupiter, the sheer scale of this gas giant becomes overwhelming. This isn't a planet like the rocky worlds we visited. This is something entirely different, a world with no surface to land on, no solid ground to walk across. Jupiter is essentially a massive ball of hydrogen and helium, compressed by its own gravity into layers that grow stranger and more exotic the deeper we descend. The journey to Jupiter takes us past its retinue of moons, dozens of them, each a world unto itself. We catch glimpses of Io, its surface painted in yellows and oranges, the most volcanically active body in the entire solar system. We see Europa, wrapped in a shell of ice that might hide a liquid ocean beneath, an ocean that could potentially harbor life. Ganymede looms large, bigger than the planet Mercury, with its own magnetic field. Callisto appears ancient and cratered, its surface unchanged for billions of years. But we're not stopping at these moons. We're heading straight into Jupiter itself. The outer edges of Jupiter's atmosphere greet us first, so tenuous that it's hard to say exactly where space ends and the planet begins. But soon we're enveloped in clouds, and the first thing that strikes you is the color. Bands of white and brown and tan stretch horizontally around the planet, each band a river of wind flowing at different speeds. These bands are organized by latitude, with zones of rising gas appearing bright white, and belts of descending gas appearing darker brown and red. The winds here are ferocious, reaching speeds of 600 kilometers per hour in some regions. These aren't temporary weather systems like hurricanes on Earth. These are permanent features of Jupiter's atmosphere, driven by the planet's rapid rotation. Jupiter spins once every 10 hours, faster than any other planet in the solar system, and this rapid rotation creates powerful forces that organize the atmosphere into these distinct bands. We descend deeper, and the great red spot looms before us, a storm system that has raged for at least 300 years, possibly much longer. This anticyclonic storm is so large, you could fit 2 or 3 Earths inside it. The winds at its edges reach speeds of 400 kilometers per hour, swirling around a high-pressure center. The reddish color comes from complex organic molecules created by ultraviolet light from the sun. Though the exact chemistry is still not fully understood, we plunge into the storm, and the turbulence is incredible. Updrafts and downdrafts create violent vertical motion. Lightning flashes illuminate the clouds from within, bolts of electricity far more powerful than anything on Earth. The storm extends deep into Jupiter's atmosphere, perhaps hundreds of kilometers down, driven by heat rising from the planet's interior. This is weather on a scale that makes Earth's hurricanes look like gentle breezes. As we continue our descent, the temperature and pressure begin to rise dramatically. The thin upper clouds give way to thicker layers. Ammonia ice crystals form the highest clouds, creating those white zones we saw from above. Below them, ammonium hydrosulfide clouds form a darker layer. Deeper still, water clouds form, though we can only infer their existence because we can't see this deep into Jupiter's atmosphere from the outside. The pressure builds steadily as we sink. At 100 kilometers below the cloud tops, the atmospheric pressure equals Earth's sea level pressure. At 200 kilometers, it's doubled. The temperature rises too, reaching comfortable room temperature at certain depths, creating a layer where the pressure and temperature would theoretically allow humans to exist, if only there was something to stand on. But there isn't. There's just more and more atmosphere pressing down from above. We continue sinking, and around 1,000 kilometers deep, something remarkable happens. The pressure becomes so intense that hydrogen begins to behave differently. Under normal conditions, hydrogen is a gas, with individual molecules bouncing around freely. But under extreme pressure, those molecules are forced closer and closer together until they start to form a liquid. We're entering Jupiter's liquid hydrogen ocean, a sea with no surface, No waves, just an endless expanse of liquid hydrogen that extends thousands of kilometers down. The transition from gas to liquid isn't sharp like water boiling on a stove. Instead, it's gradual, a continuous change as the pressure increases. The density slowly increases, the viscosity changes, and eventually you're swimming through liquid rather than flying through gas. This liquid hydrogen ocean is one of the strangest features of Jupiter, a sea that exists nowhere on Earth, because we can't create the pressures necessary to liquefy hydrogen under these conditions. We sink deeper still, thousands of kilometers into Jupiter's interior, and the pressure continues to build. At around 20,000 kilometers deep, we reach a pressure of 2 million Earth atmospheres. Here, something even stranger occurs. The pressure is so immense that hydrogen is forced into a state that doesn't exist anywhere else in the solar system, except in the cores of the other giant planets. The electrons are stripped away from the hydrogen atoms, creating a fluid that conducts electricity like a metal. This is metallic hydrogen, a substance that scientists have tried to create in laboratories on Earth, but have only managed to produce for microseconds before it explodes. This metallic hydrogen ocean extends for thousands of kilometers, and it's here that Jupiter's powerful magnetic field is generated. Electric currents flowing through this metallic hydrogen create a magnetic field 14 times stronger than Earth's, extending millions of kilometers into space. This magnetic field traps charged particles from the solar wind, creating radiation belts so intense they would kill an unprotected human in minutes. It's this magnetic field that creates Jupiter's spectacular auroras, glowing ribbons of light at the poles, far more powerful than Earth's northern and southern lights. We continue our descent through the metallic hydrogen, feeling the temperature climb to 10,000 degrees Celsius, as hot as the surface of the sun. The pressure here exceeds 40 million Earth atmospheres, crushing beyond anything we can truly comprehend. And yet we continue deeper, toward Jupiter's core, the mysterious heart of this giant world. Scientists have debated for decades about what lies at Jupiter's center. Early models suggested a small rocky core, perhaps 10 to 15 times Earth's mass, made of heavy elements that sank to the center during Jupiter's formation. More recent data from the Juno spacecraft suggests something more complex, possibly a diluted core where rock and metallic hydrogen are mixed together, or perhaps no distinct core at all, just a gradual transition to denser materials. As we approach the center, we might find a region enriched in heavy elements like iron, silicon, and oxygen, but not formed into a solid ball the way Earth's core is. The temperature here could reach 30,000 degrees Celsius, and the pressure might exceed 50 million Earth atmospheres. The conditions are so extreme that our understanding of how matter behaves breaks down. We're in a realm where quantum effects become important, where the normal rules of chemistry and physics need to be reconsidered. Emerging from the other side of Jupiter, we look back at this magnificent giant, a world that contains more mass than all the other planets combined, a world whose gravity shaped the entire solar system. Jupiter's powerful gravitational field has acted as both protector and destroyer. It has flung countless comets and asteroids out of the solar system, or crashed them into the sun, protecting the inner rocky planets from bombardment. But it has also prevented the formation of another planet in the asteroid belt, its gravity stirring up the region so much that planetesimals could never coalesce into a larger world. We leave Jupiter behind and continue outward to Saturn, the jeweled planet, the crown of the solar system. From a distance, Saturn appears serene, wrapped in its famous rings that extend hundreds of thousands of kilometers, but are less than a kilometer thick in most places. These rings aren't solid. They're made of countless individual chunks of ice and rock, ranging from particles smaller than a grain of sand to boulders the size of houses, all orbiting Saturn in a flat disk. As we approach, the rings become more detailed. We can see gaps in the rings, divisions carved by the gravitational influence of Saturn's many moons. The Cassini division is the largest gap, a region 4,000 kilometers wide, where the rings thin out dramatically. The Encke gap is narrower, only 300 kilometers wide, kept clear by a small moon called Pan that orbits within the gap, sweeping up particles like a cosmic vacuum cleaner. We pass through the rings, and the experience is otherworldly. Chunks of ice tumble around us, each one reflecting sunlight, creating a glittering field of frozen debris. Some pieces are pure ice, white as snow. Others are dirty ice, stained by rocky impurities. The rings aren't uniform. They're divided into thousands of narrow ringlets, each one slightly different in composition and density, creating a structure as complex as a vinyl record when viewed up close. But we're not here to explore the rings. We're diving into Saturn itself, and as we approach the cloud tops, we see a world similar to Jupiter, but somehow more subdued, more elegant. The bands are there, the zones and belts organized by latitude, but they're hazier, less distinct. The colors are more muted, pale yellows and creams and tans. There's no great red spot on Saturn, though there are occasional massive storms that erupt and encircle the entire planet in bands of white clouds. We descend through the upper atmosphere, and immediately we notice how cold it is. Saturn is nearly twice as far from the Sun as Jupiter, and it receives only about 1/4 as much sunlight. The cloud tops are frigid, minus 140 degrees Celsius. The atmosphere is similar to Jupiter's, mostly hydrogen and helium with traces of methane and ammonia, but the colder temperatures mean the clouds form at different altitudes, creating Saturn's distinctive hazy appearance. As we sink deeper, the pattern is familiar from Jupiter. The pressure and temperature rise. Ammonia ice clouds give way to ammonium hydrosulfide clouds, and then water ice clouds. The winds are powerful here too, reaching 1,800 kilometers per hour at the equator, even faster than Jupiter's winds. These super-rotating winds create a hexagonal pattern at Saturn's North Pole, a bizarre geometric formation that has existed for decades. Each side of the hexagon is wider than Earth's diameter, and the mechanism that creates and maintains this shape is still not fully understood. We continue our descent through Saturn's atmosphere, and around 1,000 kilometers deep, we enter the liquid hydrogen ocean, just as we did on Jupiter. The transition is gradual, the gas becoming denser and denser until it's clearly a liquid. We sink through thousands of kilometers of this liquid hydrogen, the pressure building, the temperature rising. At around 30,000 kilometers deep, we reach the metallic hydrogen layer, where hydrogen conducts electricity and generates Saturn's magnetic field. Saturn's magnetic field is weaker than Jupiter's, only about 20 times stronger than Earth's field, but it's still powerful enough to create magnificent auroras at the poles. These auroras are visible in ultraviolet light, glowing ribbons that dance across the polar regions, energized by particles from the solar wind and from Saturn's moon Enceladus, which spews water vapor into space from geysers at its south pole. We continue through the metallic hydrogen, feeling the temperature climb to 15,000 degrees Celsius. The pressure here exceeds 60 million Earth atmospheres. And somewhere deep within Saturn, perhaps at the very center, there might be a core of heavy elements, rock and metal compressed to unimaginable densities. Or perhaps, like Jupiter, Saturn has a diluted core, a fuzzy boundary where heavy elements gradually give way to metallic hydrogen. The core, if it exists as a distinct entity, might be 10 to 20 times Earth's mass, but spread over a region larger than Earth itself. The temperature at the center could reach 20,000 degrees Celsius, and the pressure might approach 80 million Earth atmospheres. We're at the limit of what our current physics can reliably predict. The behavior of matter under these conditions is still an active area of research, with scientists using powerful computers to simulate the quantum interactions of atoms under extreme pressure and temperature. Emerging from Saturn, we take a moment to appreciate what we've just experienced. These gas giants, Jupiter and Saturn, represent a different class of planet entirely from the rocky worlds of the inner solar system. They're mostly hydrogen and helium, the same elements that make up the Sun, and in a sense they're failed stars. Worlds that didn't quite gather enough mass to ignite nuclear fusion in their cores. If Jupiter had been about 80 times more massive, it would have become a star, and our solar system would have been a binary star system with 2 suns. But our journey isn't over. We continue outward to the ice giants Uranus and Neptune, worlds that are smaller than Jupiter and Saturn, but still enormous compared to Earth. These planets have a different composition, with much more water, methane, and ammonia mixed with their hydrogen and helium. They're colder, stranger, and in some ways even more mysterious than the gas giants we've just visited. Uranus appears before us, a pale blue-green sphere tipped on its side. Unlike every other planet, which spins roughly upright, Uranus rotates on its side, its axis tilted 98 degrees. This means that for part of its 84-year orbit around the Sun, one pole points directly at the Sun, while the other pole faces eternal darkness. Then, 42 years later, the situation reverses. This strange tilt was probably caused by a massive collision early in Uranus's history, an impact so violent it knocked the entire planet over. As we approach, we see that Uranus is remarkably bland compared to Jupiter and Saturn. There are few visible cloud features, just a smooth blue-green disk. The color comes from methane in the upper atmosphere, which absorbs red light and reflects blue and green. The lack of visible features doesn't mean Uranus is inactive. It just means that whatever weather systems exist are hidden beneath thick layers of haze. We begin our descent, and the upper atmosphere is incredibly cold, minus 220 degrees Celsius, the coldest planetary atmosphere in the solar system. The atmosphere is mostly hydrogen and helium, but with a much higher proportion of methane than Jupiter or Saturn. As we descend, the temperature slowly rises, but Uranus generates very little internal heat compared to the other giant planets, while Jupiter and Saturn radiate more heat than they receive from the Sun. Uranus radiates almost nothing, making it colder than it should be at this distance from the Sun. We pass through the relatively thin atmospheric layer, only a few thousand kilometers deep, and enter a realm that scientists call the mantle, though it's nothing like Earth's rocky mantle. This is a hot, dense fluid made of water, methane, and ammonia, compressed to enormous pressures. Under these conditions, water doesn't behave like the liquid we're familiar with. It's a superionic ice, a bizarre state where oxygen atoms are locked in a solid crystal lattice, while hydrogen ions flow freely through that lattice, conducting electricity. This superionic ice ocean extends for thousands of kilometers, and it's thought to be the source of Uranus's magnetic field. But that magnetic field is strange, tilted 60 degrees from the planet's rotation axis, and offset from the center. The field wobbles wildly as Uranus rotates, creating a corkscrew shape that's unlike any other planetary magnetic field in the solar system. We sink deeper through this exotic ocean, passing through regions where the pressure exceeds 2 million Earth atmospheres and the temperature climbs to 5,000 degrees Celsius. And at the very center of Uranus, there might be a small rocky core, perhaps half an Earth mass of iron and silicate rock, compressed to incredible densities. Or perhaps there's no distinct core at all, just a gradual transition to denser materials. Emerging from Uranus, we continue outward to our final destination, Neptune, the most distant planet in our solar system since Pluto's reclassification. Neptune appears as a deeper, richer blue than Uranus, colored by methane, but somehow more vibrant, more alive. As we approach, we immediately see that Neptune is far more active than Uranus, despite being farther from the Sun and receiving even less sunlight. Great dark spots appear in Neptune's atmosphere, massive storm systems similar to Jupiter's Great Red Spot. White clouds of methane ice float high above the main cloud deck, casting shadows on the layers below. Wind speeds here are the fastest in the solar system, reaching 2,000 kilometers per hour, faster than the speed of sound on Earth. How Neptune generates enough energy to drive these incredible winds is still a mystery, because like Uranus, Neptune should be too cold and too far from the Sun to have such active weather. We descend into Neptune's atmosphere, and the structure is similar to Uranus. A relatively thin atmospheric layer gives way to a deep ocean of supersonic ice, a mixture of water, methane, and ammonia compressed to exotic states. Neptune's magnetic field is also tilted and offset, creating a complex field structure that wobbles as the planet rotates. And deep within Neptune, there might be a rocky core, perhaps slightly larger than Uranus's core, compressed to unimaginable densities by the weight of the entire planet pressing down from above. As we emerge from Neptune and look back at the 8 worlds we've visited, the diversity is staggering. From the scorched surface of Mercury to the frozen depths of Neptune, from the toxic clouds of Venus to the metallic hydrogen oceans of Jupiter, each planet tells a unique story about how worlds form and evolve. Our solar system is a laboratory of planetary science, showing us the full range of possibilities that exist when gas and dust collapse under gravity to form new worlds. But there's something humbling about this journey too. We've traveled through planets that would instantly destroy any spacecraft we could build. We've experienced temperatures that would vaporize steel and pressures that would crush diamonds. We've seen storms that have raged for centuries and magnetic fields that could scramble electronics from millions of kilometers away. The solar system is beautiful, but it's also hostile, a reminder that Earth's gentle climate and breathable atmosphere are precious beyond measure. As we drift away from Neptune, the solar system spreads out before us like a cosmic map, each planet now a memory etched into our consciousness. The journey we've taken tonight exists only in imagination, yet it reveals truths about our cosmic neighborhood that telescopes and spacecraft have spent decades uncovering. We've touched worlds that no human hand will ever reach, descended through atmospheres that would dissolve our bodies in seconds, and witnessed the alien beauty of planets that challenge everything we thought we knew about how worlds should behave. Think about what we've experienced together. Mercury taught us about extremes, how a world can bake and freeze on the same day, how ancient impacts can ring a planet like a bell. Venus showed us the dangers of runaway climate change, a cautionary tale written in sulfuric acid clouds and temperatures hot enough to melt lead. Earth reminded us of the miracle of life, the delicate balance of conditions that allow liquid water and breathable air, and all the complexity that emerges from those simple ingredients. Mars whispered stories of lost potential, of rivers that once flowed and atmospheres that escaped to space. Jupiter overwhelmed us with its scale, a world so massive it shapes the orbits of everything around it. a planet that's almost a star but not quite. Saturn dazzled us with its rings, those impossibly thin disks of ice and rock that encircle the planet like a cosmic halo. Uranus surprised us by lying on its side, a world knocked askew by some ancient violence. And Neptune, distant and deep blue, showed us that even in the cold outer reaches of the solar system, winds can howl faster than sound. But here's what makes this journey truly remarkable. Everything we've described, every detail about temperatures and pressures and compositions, comes from real data gathered by real spacecraft and real telescopes operated by real humans who dedicated their lives to understanding these distant worlds. The Mariner missions flew past Mercury and Venus in the 1960s and 70s, sending back the first close-up images of those scorched and shrouded worlds. The Viking landers touched down on Mars in 1976, analyzing Martian soil and searching for signs of life. Voyager 1 and 2 performed their grand tour of the outer planets in the late 70s and 80s, flying past Jupiter, Saturn, Uranus, and Neptune, sending back images that transformed these distant lights into real places with weather and moons and mysteries. The Galileo spacecraft orbited Jupiter for 8 years, diving into its atmosphere in a final suicide mission that revealed new layers of complexity. Cassini spent 13 years at Saturn, discovering geysers on Enceladus and lakes of liquid methane on Titan before plunging into Saturn's atmosphere in 2017. These missions, these robotic explorers, have been our eyes and ears in places we cannot go. They've measured temperatures with thermometers, analyzed atmospheres with spectrometers, mapped magnetic fields with magnetometers. Every fact we've shared tonight represents years of work by teams of scientists and engineers who built these spacecraft, launched them on rockets, guided them across billions of kilometers of space, and decoded the radio signals they sent back to Earth. And yet, despite all this knowledge, mysteries remain. We still don't fully understand Jupiter's core or why Neptune is so much more active than Uranus. We don't know exactly how Saturn's hexagonal storm maintains its shape or what creates the super-rotating winds on Venus. We haven't definitively answered whether Mars ever had life or whether Europa's subsurface ocean could harbour living organisms today. The solar system keeps surprising us, revealing new puzzles even as we solve old ones. This is what makes planetary science so captivating. Every mission answers some questions, but raises new ones. Every new telescope reveals details we couldn't see before, details that don't quite fit our models, details that force us to rethink our assumptions. The solar system is a dynamic place, constantly changing on timescales from seconds to billions of years, and we're privileged to live in an era when we can study it up close. Consider the human element of all this. When we sent Voyager past Neptune in 1989, the spacecraft was navigating by starlight, using its cameras to photograph distant stars and calculate its position. The radio signals took 4 hours to travel from Neptune back to Earth, so controllers couldn't steer the spacecraft in real time. They had to program everything in advance, trusting that their calculations were correct, hoping that nothing unexpected would go wrong, and it worked. Voyager 2 flew through Neptune's system exactly as planned, discovering new moons and rings and capturing images of a world no one had ever seen up close before. That mission happened over 3 decades ago, and Voyager is still sending data back to Earth, now exploring interstellar space beyond the influence of the Sun. It carries a golden record with sounds and images from Earth, a message to any alien civilization that might someday find it drifting through the galaxy. That record includes greetings in dozens of languages, music from different cultures, photographs of people and places and natural wonders. It's a time capsule from humanity, a reminder that we exist, that we wonder about the universe, that we dream of making contact with other minds among the stars. The golden record also reminds us of something important. We're not just passive observers of the universe. We're participants in a cosmic story that began with the Big Bang and will continue long after our sun burns out. The atoms in our bodies were forged in ancient stars that exploded billions of years ago. The iron in our blood, the calcium in our bones, the oxygen we breathe, all of it came from stellar furnaces that converted hydrogen into heavier elements through nuclear fusion. We are literally made of stardust, temporary arrangements of matter that have somehow become aware of their own existence. This awareness, this consciousness, allows us to appreciate the beauty and complexity of the solar system in ways that purely physical processes cannot. A storm on Jupiter doesn't know it's beautiful. The rings of Saturn don't marvel at their own delicate structure, but we do. We look at images from spacecraft and feel wonder. We study the data and piece together stories about how these worlds formed and evolved. We imagine what it would be like to float through Jupiter's clouds or stand on the surface of Mars watching the sun set in a butterscotch sky. And tonight, we've taken that imagination one step further. We've done the impossible, descending through every planet, experiencing conditions that would kill us instantly, seeing things that no camera could ever capture. This journey exists only in our minds, but that doesn't make it less valuable. Imagination is how we explore possibilities, how we test ideas, how we dream of futures that don't exist yet. Every spacecraft that's ever flown to another planet started as an imagination, an idea in someone's mind that gradually took shape as drawings and models, and finally as real hardware that could survive launch and navigate through space. The engineers who designed these missions had to imagine all the things that could go wrong. What if a solar panel doesn't deploy? What if the radio antenna gets stuck? What if the thrusters misfire or the computer crashes or a micrometeorite punches a hole in a fuel tank? They had to think through every possible failure mode and design backup systems and redundancies. They had to imagine success too, picturing the spacecraft arriving at its destination, executing its observations, sending data across millions or billions of kilometers back to Earth. This kind of systematic imagination, this ability to envision complex systems and predict how they'll behave, is what allows us to explore the solar system without leaving Earth. We send robots to do the exploring for us, machines that can withstand radiation and extreme temperatures and crushing pressures that would destroy biological organisms. These robots are our proxies, our representatives in hostile environments, gathering data that we analyze to build understanding. But robots have limitations. They can only measure what they're designed to measure. They can only go where we send them. They can't improvise or adapt the way a human explorer could. That's why some people dream of sending humans to Mars, of establishing permanent bases on the Moon, of someday building spacecraft that could take people to the outer planets. These dreams face enormous challenges, technical and financial and biological. The radiation exposure alone would be life-threatening. The psychological effects of spending years in a cramped spacecraft millions of kilometers from home would test anyone's sanity. And yet, the dream persists. There's something deeply human about wanting to go places ourselves, to see things with our own eyes rather than through cameras, to touch alien soil with our own hands rather than through robotic manipulators. Maybe future generations will develop technologies that make such journeys possible. Maybe they'll find ways to protect astronauts from radiation, to generate artificial gravity, to recycle air and water and grow food in space. Maybe they'll build fusion rockets or antimatter drives or some propulsion system we haven't imagined yet that could cut travel times from years to months or weeks. Or maybe humans will never physically visit the outer planets. Maybe we'll always explore through proxies, through increasingly sophisticated robots and artificial intelligence systems that can make decisions autonomously. Maybe virtual reality will become so convincing that experiencing another planet through a robot's sensors will feel as real as being there in person. The technology is already moving in that direction. Scientists can put on VR headsets and walk across the surface of Mars using data from rovers, experiencing the landscape in 3 dimensions, feeling almost as if they're really there. These technologies blur the line between physical and virtual exploration. When you're immersed in a high-fidelity simulation of Jupiter's atmosphere, watching lightning flash in the clouds around you, feeling the turbulence of updrafts and downdrafts, hearing the roar of winds, is that experience fundamentally different from being there physically? Your body is safe on Earth, but your consciousness is engaged with another world, processing information, forming memories, experiencing wonder. In some sense, you are exploring Jupiter, even if your physical body never leaves the ground. This raises philosophical questions about the nature of experience and presence. What does it mean to visit a place? Does it require physical proximity, or is it enough to gather information about that place through sensors and reconstruct it in your mind? When you look at a photograph of Saturn's rings, you're seeing light that reflected off those rings, traveled across the solar system, was captured by a spacecraft's camera, converted to digital data, transmitted to Earth, processed by computers, and displayed on a screen. The light that enters your eyes is not the same light that bounced off Saturn's rings, yet somehow you feel connected to that distant place. This chain of information transfer is what allows us to know anything about the universe beyond our immediate surroundings. We're always interpreting signals, whether it's light from distant galaxies or radio waves from spacecraft or seismic waves traveling through Earth's interior. We never experience reality directly. We experience our brain's interpretation of signals received through our senses. In that sense, all experience is virtual, a mental model constructed from incomplete information. But some models are more accurate than others. The scientific method gives us tools for testing our models against reality, for distinguishing between accurate representations and wishful thinking. When multiple independent lines of evidence all point to the same conclusion, we can be confident that our model reflects something real about the universe. The composition of Jupiter's atmosphere isn't just speculation. It's based on spectroscopy, on measurements from the Galileo probe, on theoretical calculations that match observations. The model might not be perfect, but it's grounded in data, refined through decades of study. This accumulation of knowledge is one of humanity's greatest achievements. Each generation builds on the work of previous generations, adding new observations, refining theories, correcting errors. The process is gradual, sometimes frustratingly slow, but it's reliable. The knowledge we have about the solar system today is vastly more detailed and accurate than what we knew 50 years ago. And 50 years from now, our descendants will know even more. They'll have visited places we can only imagine, answered questions we haven't thought to ask, discovered phenomena that will surprise and delight them. And they'll still have mysteries to solve. The universe is vast and complex, and there's no reason to think we'll ever reach a point where we understand everything. There will always be new frontiers, new questions, new challenges that push the limits of our knowledge and technology. That's not a failure, it's a feature. The universe is interesting precisely because it's not simple. because it rewards curiosity with endless discoveries. As we conclude our journey through the solar system, it's worth reflecting on what we've learned. Not just facts about planetary atmospheres and core compositions, but something deeper about the nature of exploration itself. We've seen that the solar system is diverse beyond imagination, that each planet has its own personality, its own story to tell. We've recognized that human curiosity drives us to explore even when there's no immediate practical benefit, that we build spacecraft and telescopes because we want to know what's out there, because we can't help but wonder. We've acknowledged the limitations of our current technology while dreaming of future advances that might overcome those limitations. We've appreciated the work of thousands of scientists and engineers who've dedicated their careers to expanding human knowledge. And we've experienced, if only in imagination, the humbling realization that Earth is special, that our planet's combination of conditions suitable for life is rare and precious, that we should protect and cherish this world that gave rise to us. The journey through every planet has taken us from the scorching surface of Mercury to the frozen depths of Neptune, through atmospheres thick and thin, through oceans of liquid hydrogen and supersonic ice, through cores of metal compressed to impossible densities. We've experienced conditions that span thousands of degrees in temperature and millions of atmospheres in pressure. We've seen weather systems that dwarf anything on Earth and magnetic fields that stretch millions of kilometers into space. And through it all, we've carried with us the knowledge that this journey, while impossible in reality, represents real places that exist right now, orbiting the same sun that warms our faces on Earth. Those planets are out there, spinning through space, their atmospheres churning, their cores cooling, their surfaces being slowly reshaped by impacts and volcanism and the patient work of geological time. They don't care that we exist. They don't notice our spacecraft or our telescopes or our curiosity. They simply are, following the laws of physics, moving through their orbits, existing as they have for billions of years and will continue to exist for billions more. But we care, we notice, we wonder, and that makes all the difference. The universe doesn't need us to observe it, but observation gives meaning to existence in a way that pure physical processes cannot. When we look at Saturn's rings and feel awe, we're adding something to the universe that wasn't there before, a subjective experience, a moment of consciousness appreciating beauty. These moments are fleeting, lasting only as long as we do, but they're real, and they matter, at least to us. So as you prepare to drift off to sleep tonight, carried gently by the rhythm of your breathing, remember that you've traveled farther than any human has ever gone. You've descended through worlds that would destroy spacecraft in seconds. You've witnessed phenomena that challenge our understanding of physics. You've imagined the unimaginable and made it feel real, if only for a moment. The solar system is vast and strange and beautiful, and you wonders tonight. Jupiter's great red spot will keep swirling. Saturn's rings will keep orbiting. Neptune's winds will keep howling through that deep blue atmosphere. And somewhere, a spacecraft will keep transmitting data across the vast emptiness of space, adding new details to our understanding, answering old questions and raising new ones. The journey continues, not just for spacecraft and scientists, but for anyone who looks up at the night sky and wonders what's out there. Every time you see a bright point of light moving against the stars, you might be seeing Jupiter, or Saturn, or Mars. Those aren't just lights. They're worlds, places with landscapes and weather and histories that stretch back billions of years. And now you know a little more about what they're really like, about what makes each one unique, about the incredible diversity that exists in our cosmic neighborhood. Fly through every planet in our solar system. Sleep finds us in different ways, sometimes gradually like the fading of daylight, other times suddenly like a switch being flipped. But wherever you are right now, whatever time it is in your corner of the world, you've journeyed through impossible distances tonight. You've touched the face of worlds that exist only as points of light in our telescopes, transformed them from distant abstractions into places with texture and depth and character. There's something profound about understanding scale. When we say Jupiter is 300 times more massive than Earth, the number doesn't capture the reality. But when you imagine descending through layer after layer of atmosphere, sinking through thousands of kilometers of liquid hydrogen, falling through metallic hydrogen oceans that conduct electricity like copper wire, suddenly that mass becomes tangible. You feel it pressing down from every direction, that enormous weight of a world so large, it almost became a star. The same applies to temperature. Saying Venus is 470 degrees Celsius tells you it's hot. But imagining the surface glowing dull red, hot enough that certain metals would puddle on the ground like water, hot enough that lead would boil away into vapor, that makes it real. These aren't just numbers in a textbook. They're conditions that exist right now on an actual world you could point to in the sky, and pressure. The crushing weight of 92 Earth atmospheres at Venus's surface seems abstract until you picture yourself a kilometer underwater on Earth, feeling that same pressure, knowing that going deeper would only make it worse. Then multiply that by the descent through Jupiter, where pressures reach millions of atmospheres, where the very nature of matter changes, where hydrogen stops being a gas and becomes liquid, then stops being an insulator and becomes a conductor of electricity. These extreme conditions teach us something important about Earth. Our planet sits in what scientists call the habitable zone, that narrow range of distances from the Sun where temperatures allow liquid water to exist on the surface. Too close, like Venus, and water boils away. Too far, like Mars, and water freezes solid. But it's not just about distance. Venus is roughly the same size as Earth, made of similar materials, yet its climate spiraled into a runaway greenhouse effect that created the hellscape we see today. What made Earth different? Partly luck, partly the right combination of factors that kept our climate stable for billions of years. We have plate tectonics that recycles carbon dioxide, preventing too much from building up in the atmosphere. We have a large moon that stabilizes our axial tilt, preventing wild climate swings. We have Jupiter acting as a cosmic vacuum cleaner, its powerful gravity deflecting or capturing asteroids and comets that might otherwise bombard the inner solar system. All these factors working together created conditions where life could emerge and persist. Simple single-celled organisms appeared on Earth within a few 100 million years of the planet's formation, remarkably quickly in geological terms. Those simple cells eventually evolved into the incredible diversity of life we see today, from bacteria to blue whales, from microscopic plankton to towering redwood trees. And somewhere along that evolutionary path, consciousness emerged, the ability to observe and question and wonder about the universe. That consciousness allows you to do what you've done tonight, to imagine yourself flying through planets, experiencing conditions no living thing could survive, gathering knowledge about worlds you'll never physically visit. This ability to learn about distant places through observation and reasoning, to build mental models of reality that extend far beyond direct experience, is perhaps the most remarkable feature of human cognition. Consider what it takes to understand Jupiter's interior structure. Nobody has drilled into Jupiter's core. We can't sample the metallic hydrogen directly or measure its properties in a laboratory. Yet we can deduce what must be there based on Jupiter's mass, its gravitational field, its rotation rate, its magnetic field. We can run computer simulations that model how matter behaves under extreme pressure and temperature. We can compare our predictions to observations and refine our models until they match what we see. This process of scientific inference has revealed truths about the universe that would have seemed like magic to our ancestors. They looked at Jupiter and saw a bright wandering star, important for astrology perhaps, but fundamentally mysterious. We look at Jupiter and see a world with specific composition, structure, and history. We understand how it formed from the same cloud of gas and dust that created the Sun. We know why it has moons and rings. We can predict its future evolution over billions of years. Yet even with all this knowledge, Jupiter retains its mystery. The Great Red Spot has persisted for centuries, but we still don't fully understand what sustains it, why it hasn't dissipated like storms on Earth do. The precise structure of Jupiter's core remains uncertain, with recent data suggesting it might be fuzzy or diluted rather than a distinct solid ball. The planet generates more heat than it receives from the Sun, but the exact mechanisms driving this internal heat engine are still being researched. These remaining mysteries aren't failures of science. They're invitations to deeper understanding, puzzles that motivate the next generation of missions and observations. The Juno spacecraft currently orbiting Jupiter is designed specifically to answer some of these questions, mapping the planet's gravitational and magnetic fields with unprecedented precision, peering beneath the cloud tops with instruments that can see through the thick atmosphere. Each planet we visited tonight has similar mysteries waiting to be solved. Mercury's enormous iron core suggests something dramatic happened during its formation, but we don't know exactly what. Venus lost its water billions of years ago, but we don't know if it ever had oceans like Earth, or if the water was delivered later and then lost. Mars clearly had liquid water flowing on its surface in the past, carving massive channels and possibly filling ancient ocean basins. But we don't know how long that water persisted or where it all went. The ice giants Uranus and Neptune present their own puzzles. Why is Uranus so much less active than Neptune despite receiving more sunlight? What knocked Uranus onto its side? Why do both planets have such strangely tilted and offset magnetic fields? The Voyager flybys gave us our only close-up look at these worlds. Brief snapshots taken during quick passes that lasted just days. We need new missions to return to the ice giants, to orbit them, and study them over complete seasonal cycles. These future missions will build on the legacy of exploration that began in the early space age. The first spacecraft to visit another planet was Mariner 2, which flew past Venus in 1962. That mission lasted only 42 minutes at closest approach, but it revolutionized our understanding of Venus, revealing the planet's extreme surface temperature and confirming that the thick atmosphere was mostly carbon dioxide. Every mission since then has added layers of detail, transforming Venus from a mysterious, shrouded world into a place we can describe with scientific precision. The same pattern holds for every planet. Our first glimpses were blurry and incomplete, raising more questions than they answered. But each subsequent mission brought clearer images, better data, deeper understanding. The Mariner missions gave way to Viking and Voyager. Those gave way to Galileo and Cassini and Juno and New Horizons. Each generation of spacecraft carried more sophisticated instruments, capable of measuring things their predecessors couldn't detect, and the pace of discovery continues accelerating. In the past decade, we've orbited Mercury with the Messenger spacecraft, studied Saturn's moons in detail with Cassini, flown past Pluto with New Horizons, and begun long-term observation of Jupiter with Juno. Future missions planned or under development will return samples from Mars, explore Europa's subsurface ocean, visit Neptune and Uranus, and continue pushing the boundaries of what we know about our solar system. But space exploration isn't just about accumulating facts. It's about changing perspective, about seeing ourselves and our place in the universe differently. The famous Earthrise photograph, taken by Apollo 8 astronauts orbiting the Moon, showed our planet as a fragile blue marble floating in the darkness of space. That image helped spark the environmental movement, making people realize that Earth's resources are finite, that we need to take care of our planet because it's the only one we have. Carl Sagan articulated this perspective beautifully when describing the pale blue dot photograph taken by Voyager 1 from beyond Neptune's orbit. In that image, Earth appears as a tiny speck, less than a pixel, suspended in a beam of scattered sunlight. Sagan wrote about how that dot contains everyone you love, everyone you know, every human who ever lived, all playing out their dramas on that mote of dust suspended in a sunbeam. He urged us to cherish and preserve that pale blue dot, the only home we've ever known. This cosmic perspective doesn't diminish human experience, it enriches it. Knowing that we're inhabitants of one planet among many, one solar system among billions, one galaxy among trillions, doesn't make our lives less meaningful. It makes them more precious. We're conscious beings capable of understanding our place in this vast cosmos, of appreciating beauty and creating meaning in a universe that's otherwise indifferent to our existence. The journey through every planet reminds us of both our smallness and our significance. We're tiny compared to Jupiter, fragile compared to Venus's crushing atmosphere, brief compared to the billions of years these worlds have existed. Yet we're the ones asking questions, building spacecraft, analyzing data, piecing together the story of how the solar system formed and evolved. We're the universe becoming aware of itself, matter organized in such a way that it can contemplate its own existence. This self-awareness comes with responsibility. We're the only species on Earth capable of understanding the threats facing our planet, from climate change to asteroid impacts, to the eventual death of our sun billions of years in the future. We're also the only species capable of doing anything about those threats. The knowledge we gain from studying other planets isn't just academically interesting. It's practically important for understanding how planetary climates work, how magnetic fields protect atmospheres, how impacts shape surfaces. Venus teaches us about runaway greenhouse effects. Mars shows us what happens when a planet loses its magnetic field and atmosphere. Jupiter demonstrates how gravitational interactions can stabilize or destabilize entire planetary systems. Every world we study adds to our understanding of how planets work in general, including our own. This knowledge might prove crucial for humanity's long-term survival. Some people argue that we should focus on solving Earth's problems before spending resources on space exploration. But this represents a false choice. The same technologies that enable space exploration often have terrestrial applications. Satellites monitor Earth's climate, track storms, enable global communications. Planetary science helps us understand climate change. Materials developed for spacecraft find uses in everyday products. The challenge of keeping astronauts alive in hostile environments drives innovations in recycling, life support, and sustainable living. More fundamentally, exploration is part of what makes us human. Our ancestors didn't need to cross oceans or climb mountains or explore polar regions, but they did anyway, driven by curiosity and the desire to see what was beyond the horizon. That same impulse drives space exploration today. We explore because we can, because we're curious, because the universe is fascinating and we want to understand it better. And there's a practical argument too. Eventually, Earth will become uninhabitable. The sun grows brighter over time as it ages, and in about 1 billion years, Earth's oceans will boil away. Long before that, we might face catastrophic asteroid impacts or supervolcano eruptions or other existential threats. Having the capability to live elsewhere, whether on other planets or in space habitats, provides insurance against extinction. It's the ultimate backup plan for humanity. This long-term thinking requires patience. We won't colonize Mars in the next decade or build cities on Europa in this century, but we can take steps in that direction, learning how to live off Earth, developing technologies that will be needed for permanent settlement, inspiring young people to pursue careers in science and engineering. Every mission to another planet, every robot we send to explore distant worlds, moves us closer to a future where humanity is no longer confined to a single planet. That future might seem like science fiction, but so did the idea of walking on the moon until we actually did it. So did the concept of sending spacecraft to every planet in the solar system until Voyager made it reality. So did the notion of landing rovers on Mars and driving them around for years until spirit and opportunity and curiosity and perseverance proved it was possible. What seems impossible today might become routine tomorrow, given enough time and effort and ingenuity. As you settle deeper into rest, your breathing slowing, your thoughts drifting, remember that you've touched infinity tonight. You've experienced worlds beyond imagining, descended through atmospheres that would tear apart any machine we could build, witnessed beauty and violence on scales that dwarf anything on Earth. These worlds exist independent of our observation, spinning through space according to physical laws, but your awareness of them adds something new to the universe. A moment of consciousness appreciating the vast diversity of creation. The solar system will continue its ancient dance long after you and everyone you know has returned to dust. Jupiter will keep rotating every 10 hours. Saturn's rings will keep orbiting, though they're gradually falling into the planet and might disappear in a few 100 million years. Uranus will keep rolling along its tilted axis. Neptune's winds will keep howling. Mercury will keep baking and freezing. Venus will keep crushing and burning. Mars will keep dreaming of the water it lost. Earth will keep spinning, its inhabitants hopefully learning to take better care of their precious home. And somewhere out there, beyond the planets, beyond the Kuiper Belt where Pluto orbits, beyond the scattered disk of icy bodies, beyond the Oort cloud that marks the true edge of the sun's gravitational influence, the Voyager spacecraft continue their journey into interstellar space. They're still transmitting data, still functioning after more than 4 decades in space, still carrying those golden records with messages from Earth. Someday, billions of years from now, long after the sun has swelled into a red giant and consumed the inner planets, long after it's shed its outer layers and faded to a white dwarf, long after the solar system as we know it has ceased to exist, those golden records might still be out there, drifting through the galaxy. They'll be the last remnants of our civilization, archaeological artifacts from a species that looked up at the stars and wondered what was out there, that built machines to explore places they couldn't go themselves, that imagined flying through every planet and then actually sent robots to see if they were right. That's the legacy of the journey we've taken tonight. Not just knowledge about planetary atmospheres and core compositions, but something deeper about who we are as a species, about our curiosity and creativity and determination to understand the universe we inhabit. We're explorers by nature, driven to see what's beyond the next hill, the next ocean, the next planet. That drive has taken us from caves to cities to the moon, and someday it might take us to the stars. But for now, for tonight, it's enough to have traveled in imagination through every planet in our solar system. You've experienced more than most people ever will. journeying to places that exist only as data and images and scientific models. You've made those distant worlds feel real, if only for a moment, transforming numbers and facts into visceral experience. That's the power of imagination combined with knowledge, the ability to construct mental realities that feel as vivid as anything you could touch. So rest now, knowing you've accomplished something remarkable. You've flown through Mercury's scorched landscape and Venus's toxic clouds. You've breathed Earth's gentle atmosphere and walked Mars's rusty deserts. You've descended through Jupiter's endless storms and Saturn's elegant haze. You've experienced Uranus's strange sideways rotation and Neptune's fierce winds. You've touched every world in our cosmic neighborhood, gathering them into your consciousness like precious stones, each one unique, each one beautiful in its own way. The journey ends where it began, here in this quiet moment, wherever you are, whatever time it is. The planets will still be there tomorrow, waiting for the next generation of explorers, the next wave of missions, the next person who looks up at the night sky and wonders what it would be like to visit those distant lights. And maybe someday, centuries or millennia from now, humans will actually fly through those planets, not in imagination, but in reality, using technologies we haven't invented yet, driven by the same curiosity that motivated tonight's journey. Until then, we explore through our minds and our machines, gathering knowledge piece by piece, building understanding gradually, always reaching toward mysteries just beyond our grasp. That reaching defines us as much as anything. That refusal to accept ignorance when knowledge is possible. That determination to understand even when understanding is difficult. We're the species that figured out how to split atoms and sequence genomes and send messages across the solar system at the speed of light. We're the ones who imagined flying through planets and then did the math to figure out what we'd actually experience if we could. Sweet dreams, cosmic traveler. May your rest be as peaceful as the silence between the stars, as gentle as the solar wind pushing outward from the sun, as deep as the cores of the planets you visited tonight. The universe continues its eternal motion around you, indifferent to your presence, yet somehow made more complete by your awareness of it. You are stardust that learned to wonder, atoms that somehow became conscious, a temporary pattern in the cosmic dance that will someday dissolve back into the elements from which it came. But while you exist, while consciousness flickers in your neurons and thoughts flow through your mind, you carry with you the knowledge of worlds beyond your own. You've touched the solar system tonight in ways that matter, ways that connect you to the grand story of exploration and discovery that defines our species. Rest now in that knowledge, secure in the understanding that you're part of something larger than yourself, a civilization that looks outward and asks questions and seeks answers among the planets and stars. The journey through every planet is complete. The solar system has revealed its secrets, at least the ones we currently understand. But the universe holds infinitely more mysteries, more worlds orbiting other stars, more galaxies beyond our own, more questions waiting for curious minds to ask them. Tonight, you've explored 8 planets. Tomorrow, who knows what discoveries await? What new missions will launch? What new data will arrive from distant spacecraft? What new understanding will emerge from scientists analyzing observations and running simulations? The adventure continues, not just in space, but here on Earth, in laboratories and universities and observatories, in the minds of people who dedicate their lives to understanding the cosmos. And it continues in moments like this, when someone takes the time to imagine what it would be like to fly through every planet, to experience the impossible, to transform scientific knowledge into vivid mental imagery that makes distant worlds feel close and real and meaningful. Thank you for taking this journey. Thank you for letting your imagination soar through the solar system, for caring enough about these distant worlds to spend time learning about them. The universe is vast and ancient and mostly empty, but it's also filled with wonders beyond counting, and you've experienced a few of them tonight. May that experience stay with you, enriching your understanding of our place in the cosmos, reminding you that we inhabit one small world among many, precious and fragile and worth protecting. Good night, explorer. May your dreams take you to places even more distant and strange than the planets we visited. And when you wake, may you carry with you a sense of wonder about the universe and our place in it. A reminder that we're surrounded by mysteries and beauty on scales both cosmic and intimate. The solar system is your backyard, the stars your distant neighbors, the universe your home. Never stop wondering, never stop exploring, never stop looking up at the night sky and asking what's out there. The planets are waiting. The solar system stretches out in the darkness, each world spinning in its appointed path, following the same choreography it's performed for billions of years. But our journey isn't quite finished. There's one more perspective we need to consider, one final way to understand what we've experienced tonight. Because flying through these planets, descending through their atmospheres and cores, teaches us something that goes beyond planetary science. It reveals patterns, connections, threads that tie these worlds together into a single coherent story. Think about the journey from inner to outer solar system. We started with Mercury, small and dense, mostly metal, baked by the nearby sun. Then Venus, similar in size to Earth but wrapped in a runaway greenhouse nightmare. Earth itself, the blue jewel, the only world we know that harbours life. Mars, cold and dry, holding on to memories of when it was warm and wet. These four worlds share something fundamental. They're rocky, they have solid surfaces you could theoretically stand on. They formed in the hot inner regions of the solar nebula, where metals and silicates could condense, while lighter elements were blown away by the young sun's radiation. But then we crossed an invisible boundary in space, moving beyond the frost line, that distance from the sun where temperatures dropped low enough for water ice and other volatile compounds to freeze solid during the solar system's formation. Beyond that line, planets could grow much larger because there was simply more material available. Ice and gas were far more abundant than rock and metal, and gravity could gather enormous quantities of these lighter materials into massive worlds. Jupiter and Saturn, the gas giants, are fundamentally different from the inner planets. They're mostly hydrogen and helium, the same elements that make up the sun itself. They're failed stars in a sense, worlds that gathered enough material to become enormous but not quite enough to ignite nuclear fusion in their cores. If Jupiter had been about 80 times more massive, it would have become a brown dwarf, capable of fusing deuterium. If it had been about 1,300 times more massive, it would have become a true star, fusing hydrogen and bathing the solar system in light from 2 suns instead of 1. The ice giants Uranus and Neptune represent yet another category. They're smaller than the gas giants, but still enormous compared to Earth. Their composition is different too, with much higher proportions of water, methane, and ammonia mixed with their hydrogen and helium. These compounds were abundant in the cold outer regions where these planets formed, and they give Uranus and Neptune their distinctive blue-green colours and their exotic internal structures with those superionic ice layers. This progression from rocky worlds to gas giants to ice giants isn't random. It's a direct consequence of how planetary systems form from disks of gas and dust orbiting young stars. The temperature gradient in the disk determines what materials can condense at different distances. The density of material determines how quickly planets can grow. The timing of the young star's radiation determines when the remaining gas gets blown away, ending the growth of gas giant planets. Every planetary system probably follows similar patterns, though the details vary depending on the mass of the star, the composition of the initial nebula, and random factors like where large planets migrate to after they form. Our solar system is just one example of how these formation processes play out. Astronomers have discovered thousands of exoplanets around other stars, and they show incredible diversity. There are hot Jupiters, gas giants that orbit closer to their stars than Mercury orbits our Sun. Their atmospheres heated to thousands of degrees. There are super-Earths, rocky planets larger than Earth, but smaller than Neptune, a category that doesn't exist in our solar system. There are planets orbiting binary star systems, experiencing double sunrises. There are rogue planets that don't orbit any star at all, ejected from their birth systems to wander the galaxy alone. Each of these worlds would offer its own impossible journey if we could fly through them. Imagine descending through a hot Jupiter's atmosphere, feeling temperatures climb to rival the surface of some stars. Imagine exploring a super-Earth with several times Earth's mass, where gravity would crush you long before you reach the surface. Imagine a planet orbiting a red dwarf star, tidally locked, so one side always faces the star, while the other side faces eternal darkness. The only habitable zone, a narrow ring of twilight between eternal day and eternal night. The diversity of planets in the universe probably exceeds anything we've imagined so far. There might be carbon planets where diamond forms deep underground. There might be ocean worlds covered entirely by liquid water hundreds of kilometers deep. There might be planets with atmospheres of silicon vapor or clouds of molten iron rain. The universe is vast, and the possible combinations of temperature, pressure, composition, and gravity create environments we haven't begun to explore. But tonight, we focused on the 8 planets we know best, the worlds that share our sun, that formed from the same cloud of gas and dust that created Earth. These are our siblings in a sense, born from the same parent nebula, shaped by the same physical laws, connected by the same gravitational architecture. Understanding them helps us understand ourselves, helps us see Earth not as the center of creation, but as one example of what planets can be. This perspective, this cosmic humility, is perhaps the greatest gift that planetary exploration offers. It's easy to think of Earth as special, unique, the only world that matters. And in one sense, that's true. Earth is the only planet we know that supports life. It's the only world where you can breathe the air and drink the water and watch sunsets that paint the sky in colors that exist nowhere else. But Earth is also just another planet, following the same laws of physics that govern Mercury and Jupiter and Neptune. We're not separate from the universe. We're part of it. The elements in our bodies came from stars that died billions of years ago. The water in our cells might have arrived on comets from the outer solar system. The oxygen we breathe was produced by ancient bacteria that transformed Earth's atmosphere from carbon dioxide to the nitrogen-oxygen mixture we depend on today. We exist because of a chain of cosmic accidents stretching back to the Big Bang, each link necessary, each moment building on what came before. Flying through every planet reminds us of this interconnectedness. The iron in Mercury's core might have originated in the same supernova explosion that created the iron in Earth's core. The hydrogen in Jupiter's atmosphere was forged in the first moments after the Big Bang, making it literally the oldest matter in the solar system. The methane ice on Neptune came from the same organic compounds that eventually led to life on Earth. We are all made of the same stuff, just arranged differently, shaped by different environments, following different evolutionary paths. And yet, despite these connections, each planet has developed its own character, its own personality almost. Mercury is the scarred veteran, bearing the wounds of billions of years of impacts with stoic endurance. Venus is the toxic beauty, gorgeous from a distance but deadly up close. Earth is the nurturing parent, providing everything life needs to flourish. Mars is the melancholy dreamer, remembering better days when rivers flowed and rain fell. Jupiter is the jovial giant, dominating the solar system with its mass and energy. Saturn is the elegant aristocrat, adorned with rings that sparkle in reflected sunlight. Uranus is the eccentric loner, tipped on its side, marching to its own rhythm. Neptune is the distant sage, cold and blue and endlessly mysterious. These characterizations are metaphors, of course, projections of human traits onto inhuman objects. Planets don't have emotions or personalities. They're spheres of rock and gas following orbital mechanics, shaped by gravity and thermodynamics and fluid dynamics. But we can't help anthropomorphizing them, giving them qualities that make them easier to relate to, easier to remember, easier to care about. And maybe that's not entirely wrong. Maybe seeing planets as characters in a cosmic drama helps us understand them better, helps us remember their distinctive features, helps us appreciate the narrative arc of how they formed and evolved. Because there is a story here, a genuine narrative with a beginning, middle, and ongoing development. The solar system began as a cloud of gas and dust, remnants from previous generations of stars. Gravity caused that cloud to collapse, forming the sun at the center and a disk of material around it. Within that disk, dust grains stuck together, building larger and larger clumps. These clumps collided and merged, growing into planetesimals, then protoplanets, then full-fledged planets. The process took millions of years, a violent, chaotic period when impacts were common and the young solar system was still finding its final configuration. Some of those impacts were catastrophic. The collision that created Earth's moon probably involved a Mars-sized object slamming into the proto-Earth, blasting debris into orbit that eventually coalesced into the moon. The impact that knocked Uranus onto its side must have been similarly violent, delivering so much angular momentum that the planet's rotation axis tilted by 98 degrees. Other impacts shaped crater-scarred surfaces, created the enormous basins we see on Mercury and Mars, ejected material that became moons or rings around the giant planets. Gradually, over hundreds of millions of years, the solar system settled into relative stability. The planets cleared their orbital paths of debris. The gas in the inner solar system was blown away by solar radiation, ending the growth of the rocky planets. Jupiter and Saturn migrated inward and then back outward, their gravitational interactions reshaping the distribution of smaller bodies. The late heavy bombardment, a period of intense impacts about 4 billion years ago, scarred the surfaces of the inner planets and moons, before finally subsiding as the remaining debris was cleared away. Since then, the solar system has been relatively quiet. Planets orbit in their established paths. Occasional comets or asteroids still impact planets and moons, but nothing like the chaos of the early period. The sun slowly brightens as it ages, gradually warming the inner planets over billions of years. Jupiter and Saturn continue their gravitational dance, their orbits shifting slightly over time. The solar system is dynamic, always changing, but the changes now happen on timescales of millions or billions of years, rather than thousands. This long-term stability has allowed life to develop on Earth. If Jupiter's orbit was significantly different, it might have destabilized Earth's orbit, causing wild swings in climate that would have prevented complex life from evolving. If the late heavy bombardment had continued longer, it might have sterilized Earth's surface repeatedly, never giving life a chance to gain a foothold. If Earth were slightly closer to the Sun like Venus, or slightly farther away like Mars, liquid water might not have been stable on the surface. The conditions that allowed life to emerge and persist on Earth required a remarkable combination of factors, many of them related to the structure and history of the solar system as a whole. We're here not just because Earth is in the habitable zone, but because Jupiter protected us from excessive bombardment, because the Moon stabilized our axial tilt, because plate tectonics recycled carbon dioxide and prevented runaway climate change, because a magnetic field generated by our liquid iron core deflected the solar wind and prevented our atmosphere from being stripped away. All of these factors working together created a stable environment where simple cells could evolve into complex organisms, where multicellular life could develop, where intelligence could eventually emerge. And now that intelligence looks outward, studying the planets that share our solar system, trying to understand how we fit into the larger cosmic story. We're the universe examining itself, matter that has become conscious and curious, temporary arrangements of atoms that somehow develop the capacity to wonder about their own origins. This self-reflective quality, this ability to study ourselves and our environment and ask deep questions about existence, might be the rarest thing in the universe. Life itself might be common, scattered across countless planets orbiting distant stars. But intelligent life capable of building telescopes and spacecraft and mathematical models of planetary interiors, that might be exceedingly rare. We might be alone in the galaxy, the only conscious observers in a vast, sterile cosmos. Or there might be others, civilizations on planets we can't yet detect, looking up at their own skies and wondering if anyone else is out there. We don't know. We're searching, listening for radio signals from other civilizations, analyzing the atmospheres of exoplanets for biosignatures that might indicate life. But so far, we've found nothing. The universe seems silent, empty of other voices, other minds, other explorers like us. This silence is called the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the complete lack of evidence for them. Where is everybody? Maybe we're the first, the earliest civilization to develop in our galaxy, with others yet to come. Maybe intelligence is incredibly rare, requiring such specific conditions that it almost never emerges. Maybe civilizations tend to destroy themselves shortly after developing advanced technology, through nuclear war or environmental collapse or artificial intelligence gone wrong. Maybe they're out there, but too far away for us to detect, separated by distances so vast that communication is impossible. Maybe they exist but have no interest in reaching out, content to observe without interfering. We don't have answers to these questions yet. But the search continues, and every planet we study, every moon we explore, adds to our understanding of where life might emerge and what conditions it requires. Europa's subsurface ocean makes it a candidate for life in our own solar system. Enceladus has geysers of liquid water erupting from its south pole, suggesting another potential habitat. Titan has lakes of liquid methane on its surface, and a thick nitrogen atmosphere that might support exotic forms of chemistry. Even Venus, despite its hostile surface conditions, might have habitable layers in its upper atmosphere where temperatures and pressures are more moderate. The search for life beyond Earth is one of the great scientific quests of our time, comparable to the search for the structure of DNA or the hunt for the Higgs boson. Finding even simple microbial life on another world would transform our understanding of biology and our place in the universe. It would tell us that life is not unique to Earth, that the same chemistry that created cells here can create cells elsewhere, that the universe might be teeming with living things at various stages of complexity and development. But even if we never find life beyond Earth, the journey of exploration itself has value. Learning about other planets helps us understand our own world better. Studying Venus's runaway greenhouse effect informs our understanding of climate change. Analyzing Mars's lost atmosphere teaches us about the importance of magnetic fields. Observing Jupiter's complex weather systems reveals principles of atmospheric dynamics. Every mission, every observation, every new piece of data contributes to a larger understanding of how planets work. And there's something beautiful about that accumulation of knowledge, that gradual building of understanding through careful observation and rigorous analysis. Science is a collaborative endeavor spanning generations, with each researcher adding their small contribution to a growing body of knowledge. The work started by Galileo pointing his telescope at Jupiter and discovering its moons continues today, with spacecraft orbiting that giant planet, measuring its magnetic field and peering into its depths. The observations made by early astronomers counting craters on the moon led eventually to spacecraft landing on Mars and driving across its surface. This continuity, this connection between past and present and future, gives scientific exploration a quality almost like storytelling. Each generation inherits the knowledge of previous generations and adds to it, passing along an ever more detailed understanding of the cosmos. The story isn't finished. It might never be finished. There will always be new questions to ask, new mysteries to investigate, new frontiers to explore. That's part of what makes science exciting. You're never done. There's always more to learn. And tonight, you've participated in that ongoing story. By imagining flying through every planet, by learning about their compositions and structures and histories, you've engaged with centuries of accumulated knowledge. You've stood on the shoulders of giants, from Copernicus, who realized Earth wasn't the center of the universe, to Newton, who discovered the laws of gravity and motion, to Einstein, who showed that space and time are intertwined, to the countless scientists and engineers who've built and operated the missions that revealed these worlds to us. Your journey tonight connects you to all of them, makes you part of that long chain of curious minds reaching toward understanding. The fact that you've spent time learning about distant planets, imagining what they're like, caring enough to follow this journey to its conclusion, that says something important about human nature. We're explorers by instinct, driven to learn and discover and push beyond known boundaries. That drive has taken us from caves to cities, from walking to flying, from Earth to the moon and beyond. Where that drive will take us in the future remains to be seen. Maybe we'll establish permanent bases on Mars, creating a backup for humanity in case something catastrophic happens to Earth. Maybe we'll mine asteroids for resources, accessing the vast mineral wealth of the solar system. Maybe we'll build space habitats, artificial worlds, where people can live without depending on planetary surfaces. Maybe we'll develop new propulsion systems that make travel to the outer planets feasible for humans. Maybe we'll detect signals from alien civilizations and make contact with other intelligent beings. Or maybe none of those things will happen. Maybe we'll remain confined to Earth, looking outward but never leaving, studying the universe through telescopes and robotic proxies. Maybe we'll face challenges that prevent us from expanding into space, economic or political or environmental constraints that keep us grounded. Maybe humanity's future lies here on Earth, focusing on taking better care of our home planet rather than reaching for others. We don't know what the future holds, But we can make choices that influence that future, choices about how we allocate resources, what we prioritize, what kind of civilization we want to build. Do we want to be a species that explores and reaches outward? Or do we want to focus inward, solving problems here before venturing elsewhere? There's no obviously right answer. Both approaches have merit. Both require difficult trade-offs and careful consideration of competing values. What's certain is that the knowledge we gain from studying other planets has value regardless of whether we ever send humans to visit them. Understanding how planetary climates work helps us address climate change on Earth. Learning how magnetic fields protect atmospheres informs our understanding of space weather and radiation hazards. Studying the geology of other worlds reveals principles that apply to Earth as well. The technology developed for space missions often finds applications in medicine, communications, materials science, and other fields. So the investment in planetary exploration pays dividends even beyond the direct scientific returns. It drives innovation, inspires young people to pursue careers in science and engineering, provides a shared sense of purpose and achievement that transcends national boundaries. When Voyager flew past Neptune, people around the world watched in wonder. When rovers land on Mars, the images are shared globally. Space exploration is one of the few human endeavors that brings people together rather than dividing them. And on a personal level, learning about other worlds expands your perspective in ways that are hard to quantify but deeply meaningful. Knowing that Saturn's rings are made of countless chunks of ice, orbiting in a flat disk, adds beauty to those images from spacecraft. Understanding that Jupiter's great red spot is a storm larger than Earth makes that oval in photographs more impressive. Realizing that the surface of Venus is hot enough to melt lead gives weight to those radar maps that peer through the clouds. Each fact you learn, each concept you understand, enriches your experience of the universe. You're not just looking at pictures of distant planets. You're seeing worlds with histories and structures and processes that you can comprehend. That comprehension transforms abstract images into places that feel almost real. Destinations you could imagine visiting, if only the technology existed and the physics allowed it. We've traveled together through 8 worlds tonight, from Mercury's scorched craters to Neptune's howling winds. Each planet revealed its secrets, layer by layer, atmosphere to core, showing us the incredible diversity our solar system contains. But more than facts and figures, more than temperatures and pressures, this journey has given us something precious, perspective on our place in this vast cosmic neighborhood. The planets will continue spinning long after you've drifted off to sleep. They'll be there tomorrow, waiting under the same stars that have watched over Earth since before humans walked upright. And maybe someday, generations from now, someone will actually fly through these worlds, not in imagination, but in reality, carrying forward the curiosity that brought you here tonight. Until then, rest well, cosmic explorer. The universe keeps dancing, and you've been part of something beautiful. I hope you had an amazing time with me here at Boring Science. I will see you tomorrow as always. Until then, stay curious, keep wondering. This is Boring Science, signing off. Cheers.